James Webb was built to look farther back in time than any telescope in history. Its mission seemed straightforward. By observing the faintest and most distant light in the universe, it would help astronomers witness the era when the first galaxies were beginning to form. Scientists expected a young universe filled with small, chaotic structures, tiny collections of stars still struggling to assemble themselves into the massive galaxies we see today. The farther Webb looked, the simpler the universe was supposed to become. Instead, it found something nobody expected. Buried within some of the deepest images ever taken, astronomers began noticing strange objects that appeared as tiny crimson points of light. At first glance, they looked unremarkable. The universe is filled with red objects. Distant galaxies often appear red because their light has been stretched by cosmic expansion during its journey across billions of years. But these objects were different. They were unusually compact, unusually bright, and unusually numerous. They quickly became known by a simple nickname, little red dots. The name sounds almost harmless, but these tiny points of light have become one of the biggest mysteries James Webb has uncovered so far. To understand why they matter, it helps to remember what Webb is actually seeing when it peers into deep space. Light does not travel instantly. Every second it moves about 186,000 miles through the vacuum of space. That sounds incredibly fast, yet the universe is so vast that even light requires immense amounts of time to cross it. The sunlight warming your face left the sun more than 8 minutes ago. The light from the nearest star beyond our solar system began its journey over 4 years ago. When Webb observes galaxies billions of light years away, it is not seeing them as they are today. It is seeing them as they existed billions of years in the past. In a very real sense, James Webb is a time machine. The farther it looks, the younger the universe becomes. Eventually, astronomers reach an era known as cosmic dawn, the period when the first generations of stars and galaxies began illuminating a universe that had previously been dark. This was one of Webb's primary targets. Scientists hoped to witness the earliest stages of cosmic construction. What they did not expect was to find objects that seemed far more mature than they should have been. Many of the little red dots appear only a few 100 million years after the Big Bang. In cosmic terms, this is astonishingly early. Imagine compressing the entire 13.8 billion year history of the universe into a single calendar year. The appearance of these objects would occur within the first days of January. They emerged at a time when galaxies should still have been assembling their first major structures. Yet some of these objects seemed surprisingly bright and surprisingly massive. Brightness in astronomy often means one of two things. Either an object contains enormous numbers of stars, or something extraordinarily energetic is happening inside it. Neither explanation seemed entirely satisfactory. If these were ordinary galaxies, they appeared too developed. If they were powered by black holes, those black holes appeared too large. The mystery deepened as researchers examined more data. Instead of finding a few isolated examples, they found many. In some surveys, little red dots appeared in quantities far greater than expected. It was as if James Webb had stumbled across an entire population of objects that previous models had failed to predict. This immediately raised an uncomfortable possibility. What if the early universe was not behaving the way astronomers thought it should? For decades, computer simulations had suggested a gradual process of cosmic growth. Small structures would form first. Those structures would merge and grow larger over time. Massive galaxies were expected to be relatively rare during the universe's earliest chapters because there simply had not been enough time for them to assemble. The little red dots seemed to challenge that picture. One explanation proposed by researchers is that many of these objects are actually galaxies hiding active supermassive black holes at their centers. As matter falls toward a black hole, it heats up and releases enormous amounts of energy. This process can make a relatively small region outshine entire galaxies. If true, the red dots might not be gigantic galaxies at all. They could be compact systems dominated by rapidly feeding black holes. But that explanation creates another problem. Supermassive black holes are not supposed to appear so quickly. The largest black holes in today's universe contain millions or even billions of times the mass of our Sun. According to conventional models, building something that large should require long periods of growth. Yet some of Webb's observations suggest that extremely massive black holes may already have existed when the universe was still in its infancy. It's a little like discovering a fully grown city in the middle of an unexplored wilderness and realizing the roads, buildings, and infrastructure should have taken centuries to construct. The city is there, you can see it clearly. The question is how it appeared so soon. Another possibility is that the little red dots are genuinely massive galaxies, packed with extraordinary numbers of stars. If that is true, then the challenge becomes even greater. It would mean galaxies somehow manage to collect matter, form stars, and grow far faster than many theoretical models predicted. Either answer leads to trouble. If they are black holes, the black holes are too large. If they are galaxies, the galaxies are too mature. And if they are some mixture of both, then the early universe may be operating through processes we still do not fully understand. This is why the little red dots have attracted so much attention. They are not merely strange objects. They sit at the intersection of several of the biggest questions in modern astronomy. How quickly did galaxies form? How rapidly can black holes grow? What did the universe actually look like during its first few 100 million years? The most unsettling possibility is that these red dots are not anomalies at all. Perhaps they are revealing a population that was always there, but remained invisible until James Webb arrived. Previous telescopes simply lacked the sensitivity to detect them. If so, the universe may have been far more crowded, far more active, and far more complex during its earliest epochs than anyone realized. And that possibility leads directly to an even larger mystery. Because if the universe was already producing compact, bright, mature-looking systems this early, then the problem extends far beyond a handful of red dots. It means entire galaxies may have been appearing much sooner than expected, and once astronomers began examining Webb's deepest observations more carefully, they discovered evidence suggesting exactly that. The little red dots were only the beginning. For decades, astronomers believed they had a reasonably good understanding of how galaxies formed. The process was never thought to be simple, but it was thought to be gradual. Following the Big Bang, the universe was filled mostly with hydrogen, helium, and dark matter. Tiny fluctuations in density acted as seeds. Gravity slowly amplified those seeds, pulling matter together over hundreds of millions and eventually billions of years. Small structures formed first. Larger structures emerged later through mergers and continuous growth. The earliest galaxies were expected to be fragile, irregular, and relatively unimpressive. James Webb had other ideas. As astronomers began analyzing Webb's deepest observations, they found something increasingly difficult to explain. Some galaxies appeared astonishingly massive at a time when the universe should barely have been old enough to build them. Instead of finding cosmic toddlers taking their first steps, Webb seemed to be finding fully grown adults wandering around a cosmic nursery. The surprise wasn't just that these galaxies existed. The surprise was when they existed. To appreciate how strange this is, imagine trying to grow a giant oak tree overnight. You plant a seed before sunset. By dawn, a massive tree towers over the landscape. The tree itself is not impossible. Oaks certainly exist. The problem is the timeline. There simply wasn't enough time for the process to unfold naturally. That is roughly how many astronomers felt when Webb started sending back data from the early universe. One of the most significant discoveries came from deep surveys such as SEERS and JADES. These programs were designed to search for the faintest and most distant galaxies ever observed. Scientists expected to find small collections of young stars gradually assembling themselves into larger systems. Instead, they found candidates that appeared surprisingly bright, surprisingly large, and surprisingly evolved. Some of these galaxies seemed to contain stellar masses comparable to galaxies that, according to many models, should not have appeared until much later in cosmic history. The numbers were difficult to ignore. According to the standard timeline, the universe is approximately 13.8 billion years old. Many of Webb's most puzzling galaxies are being observed less than 700 million years after the Big Bang. Some may be even younger. That means these objects formed during the first 5% of cosmic history. Yet several appeared capable of producing stars at extraordinary rates, building mass far faster than anticipated. This created what some researchers began calling a crisis of timing. The galaxies themselves were not violating any laws of physics. Gravity can certainly build large structures, Stars can certainly form, galaxies can certainly grow. The problem was that everything seemed to be happening too quickly. It's similar to arriving at a construction site, expecting to find a foundation and a few support beams, only to discover an entire skyline already completed. The buildings are real. The question is how the construction finished before the clock should have allowed it. One possible explanation is that astronomers initially overestimated the masses of some of these galaxies. Determining the properties of extremely distant objects is difficult. The farther an object lies, the harder it becomes to interpret its light correctly. Early observations can sometimes produce misleading estimates that later analyses refine, and in some cases, that appears to have happened. Several early candidates once thought to be extraordinarily massive were later revised downward after more detailed measurements became available. Yet even after those revisions, a substantial mystery remained. While the most extreme examples became somewhat less extreme, the overall pattern did not disappear. The early universe still appeared busier than expected. The challenge becomes clearer when we consider how galaxies actually grow. Stars are not created instantly. Gas must cool and collapse. Gravity must pull material together. New stars produce radiation and stellar winds that can actually slow further star formation by pushing gas away. Every step introduces limitations. Nature is not supposed to build gigantic systems at maximum efficiency. Yet James Webb keeps finding objects that seem remarkably efficient. Some galaxies appear to have converted enormous amounts of gas into stars in relatively short periods of time. Others seem to contain mature stellar populations earlier than expected. Instead of witnessing the beginning of galaxy formation, astronomers often find themselves looking at systems that already appear well established. This raises a deeper question. What if our assumptions about the earliest galaxies are incomplete? Perhaps galaxies formed faster than our models predicted. Perhaps gas cooled more efficiently. Perhaps star formation proceeded under conditions very different from those found in the modern universe. Or perhaps entirely new processes were operating during the universe's first few 100 million years. None of these possibilities can be dismissed easily. Another factor complicates the story even further: dark matter. Modern theories of galaxy formation rely heavily on dark matter halos. These invisible structures act like gravitational scaffolding, helping ordinary matter collect and eventually form galaxies. According to current models, larger dark matter halos require time to assemble. If Webb is finding unexpectedly massive galaxies, then either dark matter structures formed more rapidly than anticipated, or galaxies were somehow able to build themselves more efficiently within those structures. Either conclusion forces astronomers to revisit long-standing assumptions. Yet perhaps the most fascinating aspect of this mystery is that it extends beyond individual galaxies. Again and again, Webb observations hint at a broader pattern. The early universe appears populated by systems that look more organized, more luminous, and more developed than expected. It's as though cosmic history accelerated during its opening chapters. The farther Webb looks, the less primitive the universe sometimes appears. That realization has forced scientists to reconsider one of the most fundamental ideas in astronomy. For years, the earliest observable universe was imagined as a place of gradual beginnings, a slow emergence of complexity from simplicity. Webb is increasingly suggesting a more dramatic picture. Complexity may have arrived astonishingly quickly, but galaxies were only part of the problem, because hidden within many of these unexpectedly mature systems was evidence of something even harder to explain, something that should have required even more time to develop, something whose growth rates challenged some of the most established models in astrophysics. The galaxies were surprising enough. The black holes inside them were even worse. And once astronomers started measuring those black holes, they discovered a mystery that may be even more difficult to solve than the galaxies themselves. If the galaxies James Webb discovered appeared too early, then the objects hiding inside some of those galaxies create an even bigger problem, because galaxies can, at least in principle, grow quickly under the right conditions. Given enough gas, enough gravity, and enough time, stars can form in enormous numbers. The process may be faster than expected, but it is not impossible. Black holes are different. The largest black holes in the universe are among the most extreme objects known to science. Some contain millions, billions, or even tens of billions of times the mass of the Sun. They sit at the centers of galaxies, controlling the motion of stars across enormous distances and powering some of the brightest phenomena ever observed. The problem is that these monsters are not supposed to appear overnight, and yet James Webb keeps finding evidence that something very close to that may have happened. To understand why this is such a serious challenge, we need to begin with a simple question. Where do supermassive black holes come from? For decades, astronomers assumed they followed a relatively straightforward path. A massive star reaches the end of its life. It collapses under its own gravity and forms a black hole. That black hole then grows by consuming surrounding gas, dust, stars, and occasionally merging with other black holes. Given enough time, a small black hole can eventually become a much larger one. The keyword is time. Even under favorable conditions, growth is not unlimited. As matter falls toward a black hole, it heats up dramatically. The resulting radiation pushes outward against incoming material. This creates a natural bottleneck known as the Eddington limit, which effectively places a speed limit on how quickly many black holes can grow. Astronomers spent years calculating these growth rates, and according to those calculations, some of Webb's discoveries simply do not make sense. The telescope has revealed evidence of active galactic nuclei and quasars existing when the universe was only a few 100 million years old. These objects are powered by black holes consuming enormous amounts of matter. The brightness alone suggests black holes of astonishing size. The issue is not that the black holes exist. The issue is how they became so large so quickly. Imagine finding a newborn city with a skyscraper already standing at its center. Not a building under construction, not a half-finished framework, a completed tower dominating the skyline. The obvious question would be, when was there time to build it? Astronomers are asking exactly the same. Some Webb observations suggest black holes with masses reaching millions or even hundreds of millions of solar masses less than 1 billion years after the Big Bang. According to conventional growth models, there simply should not have been enough time available. This has forced researchers to consider increasingly dramatic possibilities. One idea involves what scientists call black hole seeds. Perhaps the first generation of stars, known as population 3 stars, were far larger than anything commonly seen today. Some models suggest these primordial stars could have reached hundreds of times the Sun's mass before collapsing. If true, they would leave behind unusually large black hole seeds, giving future growth a significant head start. The problem is that even this may not be enough. A head start helps, but many of Webb's observations still seem difficult to reconcile with standard growth rates. Even starting with a larger seed, some black holes appear to have gained mass at extraordinary speeds. This has led to another possibility. Maybe some black holes never started as stars at all. Instead of forming from stellar collapse, certain regions of the early universe may have experienced direct collapse. Under very specific conditions, enormous clouds of gas could have bypassed star formation entirely and collapsed straight into massive black holes. In this scenario, nature skips several steps. Rather than building a small black hole and slowly growing it over hundreds of millions of years, the universe creates a massive seed almost immediately. It's a radical idea, yet increasingly astronomers are taking it seriously. The early universe may have been a far stranger place than previously imagined. Gas densities were higher, temperatures were different, radiation fields were different. The rules governing structure formation may have allowed processes that are exceedingly rare, or perhaps impossible, in the modern universe. James Webb is providing evidence that forces researchers to explore these possibilities. But there is another twist. Some observations suggest that black holes and galaxies may have evolved together much earlier than expected. Traditionally, astronomers viewed galaxy formation as the primary event. Galaxies form first. Black holes grow inside them later. Yet certain Webb observations hint that supermassive black holes may have played a central role from the beginning. In some systems, the black hole appears almost disproportionately large compared to the galaxies surrounding it. That raises an intriguing possibility. What if black holes were not merely passengers inside galaxies? What if they were among the architects? Some theoretical models propose that early black holes may have influenced star formation, regulated gas flows, and helped shape the development of entire galaxies. Rather than arriving late in the story, they may have been present near the beginning. If true, that would fundamentally alter how we think about cosmic history. The relationship between galaxies and black holes would no longer be a simple sequence of events. It would become a partnership, and like many partnerships, it would be difficult to determine which side came first. The deeper astronomers look, the more complicated the picture becomes. Every potential explanation solves one problem while creating another. Larger seeds help explain the masses but require unusual formation conditions. Direct collapse explains rapid growth but demands environments we have never directly observed. Faster accretion explains expansion but pushes physical limits. No single answer has emerged as the clear winner. Meanwhile, James Webb continues collecting data. Every new observation acts like another piece of a puzzle whose final image remains frustratingly unclear. What makes the mystery especially fascinating is that black holes are not isolated curiosities. They connect directly to almost every major question about the early universe. Understanding how they formed means understanding how galaxies formed. Understanding galaxies means understanding stars. Understanding stars means understanding chemical evolution, cosmic structure, and ultimately the history of everything visible around us. In other words, the black hole mystery is not a separate mystery. It sits at the center of many others, and that creates a troubling realization. If galaxies appeared too early and black holes grew too quickly, then perhaps the real problem isn't any individual object James Webb has found. Perhaps the problem is the timeline itself. Because somewhere between the first stars, the first galaxies, and the first giant black holes, there appears to be an entire chapter of cosmic history that we still do not fully understand. A chapter that seems to be missing, and that missing chapter may be one of the most important mysteries James Webb has uncovered so far. By this point, the mystery facing astronomers was becoming difficult to ignore. The little red dots appeared too early. Massive galaxies appeared too early. Giant black holes appeared too early. At first, each discovery seemed like an isolated problem that might eventually be explained away by better data or improved models. But as James Webb continued observing the distant universe, a more troubling possibility began to emerge. What if these were not separate mysteries at all? What if they were all symptoms of a much larger problem hidden within the timeline of cosmic history itself? For decades, astronomers have relied on a relatively straightforward picture of how complexity emerged in the universe. Following the Big Bang, the cosmos was simple. It contained mostly hydrogen, helium, dark matter, and small fluctuations in density. Over time, gravity slowly amplified those fluctuations, pulling matter together into larger and larger structures. The first stars formed. Those stars created heavier elements. Galaxies gradually assembled. Black holes slowly grew. Everything followed a sequence. Every stage built upon the stage before it. The process was not random, it was evolutionary. Complexity emerged step by step across hundreds of millions and eventually billions of years. James Webb is increasingly suggesting that the early universe may not have followed that neat progression as closely as we once believed. Again and again, astronomers are finding what appear to be the end products of evolution before they can clearly identify all of the intermediate steps that should have produced them. It is almost like opening a history book and discovering that entire chapters have been removed. The beginning is there, the ending is there, but much of the story connecting them seems strangely compressed. Imagine walking into a forest and finding enormous ancient trees that appear hundreds of years old. You can see the mature trunks. You can see the sprawling branches. You can see the complex ecosystem surrounding them. Yet somehow, the saplings, the young trees, and much of the growth process are missing from the record. The forest exists. The question is how it reached that state so quickly. This is essentially what Webb is revealing in the distant universe. Some galaxies appear surprisingly mature. Certain black holes appear surprisingly massive. Evidence of chemical enrichment appears surprisingly early. Each observation points towards significant development taking place during a period of cosmic history that should have been relatively young. One of the clearest examples involves the heavy elements scattered throughout some of these ancient systems. Immediately after the Big Bang, the universe contained almost no carbon, oxygen, silicon, nitrogen, iron, or other elements essential for planets and life. Those elements had to be forged later inside stars through nuclear fusion. When massive stars reached the end of their lives, They exploded and released those newly created elements back into space. Future generations of stars then formed from that enriched material, gradually increasing the chemical complexity of galaxies over time. This process should take time because multiple generations of stars must live and die before large quantities of heavy elements accumulate. Yet James Webb is finding evidence that some distant galaxies already contain surprisingly enriched environments at extremely early dates. In certain cases, astronomers are observing chemical signatures that suggest multiple cycles of stellar evolution may have already occurred. Once again, the problem is not that such enrichment is impossible. The problem is the clock. Every new layer of complexity appears to require additional time, and yet the universe keeps presenting astronomers with systems that seem more developed than expected for their age. The same pattern appears when researchers examine star formation rates. Many early galaxies seem capable of producing stars at extraordinary speeds. According to traditional models, numerous physical processes should limit how efficiently gas can collapse into stars. Radiation from young stars can disrupt surrounding gas clouds. Supernova explosions can scatter material and temporarily suppress further star formation. Feedback mechanisms are supposed to slow the process down. Nature generally imposes limits. Yet the galaxy's web is finding often appear remarkably productive, converting gas into stars with a level of efficiency that continues to surprise researchers. Of course, astronomers remain cautious. The history of sciences is filled with apparent crises that eventually disappeared as better observations became available. Some early estimates of galaxy masses have already been revised downward. New data continues to refine our understanding of these distant objects. It is entirely possible that some of the tension between observations and theory will weaken over time. But even after numerous corrections, a significant pattern remains. The early universe continues to look unexpectedly active. The farther Webb looks, the less primitive the cosmos sometimes appears. That realization has forced scientists to reconsider a possibility that would have seemed much more radical only a few years ago. Perhaps some of the assumptions built into our models of early cosmic evolution are incomplete. Modern cosmological simulations are among the most sophisticated scientific tools ever created. They incorporate gravity, dark matter, gas dynamics, star formation, black hole growth, and countless other physical processes. Many of their predictions have been remarkably successful. They reproduce large-scale structures across the universe with impressive accuracy. Yet simulations are only as good as the information fed into them. If a critical process is missing or underestimated, the resulting picture may differ from reality in important ways. History offers many examples of this. The Milky Way was once thought to contain the entire universe until astronomers discovered countless other galaxies beyond it. The visible matter in galaxies once appeared sufficient to explain their behavior until evidence for dark matter emerged. Dark matter itself seemed capable of explaining cosmic expansion until the discovery of dark energy introduced an entirely new mystery. Again and again, humanity has believed it possessed a relatively complete picture of the cosmos, only to discover another hidden layer waiting beneath the surface. James Webb may be exposing another one of those layers now. What makes the missing evolution problem so fascinating is that it touches nearly every major question in astronomy. It is not simply about galaxies or black holes or stars. It is about the speed at which complexity emerged throughout the universe. If the earliest structures evolved faster than expected, then countless assumptions about cosmic history may require adjustment. The challenge is not that the observations are impossible. The challenge is that so many observations seem to be pointing in the same direction. The universe appears to become organized remarkably quickly. And if galaxies and black holes were already evolving at such astonishing speeds, an even bigger question naturally follows. Individual galaxies are only small pieces of a much larger cosmic architecture. They belong to clusters, filaments, and enormous structures stretching across unimaginable distances. If Webb is finding unexpectedly mature galaxies, then perhaps the larger structures surrounding them were also taking shape much earlier than anyone predicted. And that possibility leads directly to the next mystery, because James Webb is beginning to reveal evidence that some of the earliest structures in the universe may have formed far sooner than our models ever anticipated. The deeper James Webb looks into the past, the more it becomes apparent that the mystery is not limited to individual galaxies. A galaxy, after all, does not exist alone. Every galaxy belongs to a much larger cosmic environment. They gather into groups, clusters, and enormous interconnected networks stretching across hundreds of millions of light years. These vast arrangements form what astronomers call the cosmic web, one of the largest structures in existence. For decades, scientists believed they understood roughly how this web emerged. Shortly after the Big Bang, tiny fluctuations in matter density acted as seeds. Gravity slowly amplified those fluctuations over immense spans of time, drawing matter together into filaments and nodes. Small galaxies formed first. Larger systems followed. Clusters gradually assembled. The universe evolved from simplicity toward complexity. The process was expected to be slow, especially during the earliest chapters of cosmic history. James Webb is beginning to suggest that the story may not have been quite so gradual. One of the most surprising developments from Webb's observations has been the discovery of evidence pointing toward unexpectedly advanced structures existing during the universe's infancy. In several regions of deep-field observations, astronomers have identified groups of galaxies clustered together at astonishingly early epochs. These are not merely isolated galaxies floating through space. They appear to be interacting members of larger systems that may represent the earliest versions of galaxy clusters. Some researchers describe them as protoclusters, structures caught in the process of formation long before the mature galaxy clusters we see today. Yet the scale and apparent organization of some of these systems have raised important questions. Once again, the challenge is not that such structures can exist. The challenge is how quickly they appear to have emerged. To understand why this matters, imagine observing a city from an airplane. Individual buildings tell part of the story, but the arrangement of roads, districts, and neighborhoods reveals something much larger. A city requires planning, growth, and time. If you discovered a vast urban network only days after the first settlers arrived, you would immediately wonder how such complexity developed so rapidly. The same logic applies to the universe. Finding a single large galaxy is surprising. Finding multiple galaxies already gathering into larger structures is even more difficult to explain. It suggests that gravity was organizing matter across enormous distances far earlier than many models anticipated. The cosmic web itself is one of the most extraordinary features of the universe. Although often depicted in simulations, it is difficult to appreciate its true scale. Galaxies are not distributed randomly through space. Instead, they trace out immense filaments composed of dark matter, gas, and countless galaxies connected across the cosmos. Between these filaments lie enormous voids containing relatively little matter. If the universe could somehow be viewed from far enough away, it would resemble a colossal network of glowing strands stretching across unimaginable distances. Every galaxy, including our own Milky Way, exists somewhere within this structure. The web is the framework upon which the visible universe is built. According to standard cosmological models, the earliest stages of the cosmic web should have been relatively subtle. The first filaments and nodes would gradually strengthen as gravity pulled matter inward over hundreds of millions and eventually billions of years. Yet James Webb is observing regions that already show signs of significant organization when the universe was still remarkably young. Some of these observations suggest that matter may have been gathering into large-scale structures sooner than expected. The implications are difficult to ignore because larger structures require earlier structures. If a protocluster exists, then its member galaxies had to form first. If those galaxies already contain stars and black holes, then those processes must have occurred even earlier. Every discovery seems to push the timeline further back. This is what makes the mystery so persistent. Each answer creates another question. Astronomers explain a galaxy only to encounter a black hole. They explain a black hole only to encounter a larger structure surrounding it. The deeper Webb looks, the further the origins of complexity seem to retreat into the past. It is almost like chasing a horizon that continuously moves farther away. Every time researchers think they have identified the beginning of something, they discover evidence suggesting the process started even earlier. Some scientists argue that these observations may ultimately strengthen rather than weaken existing cosmological theories. The universe is an incredibly complex system, and simulations continue to improve as new data becomes available. Small adjustments to assumptions about star formation, dark matter behavior, or gas cooling could potentially help explain some of Webb's discoveries. Others believe the telescope may be revealing gaps in our understanding of how structure formation unfolded during the first billion years of cosmic history. At the moment, no consensus exists. The debate remains active, which is precisely what makes this period in astronomy so exciting. What is becoming increasingly clear, however, is that the early universe was not a quiet place. Earlier generations of astronomers often imagined those first few 100 million years as a relatively simple era populated by primitive galaxies, slowly emerging from darkness. James Webb is painting a much more dynamic picture. Galaxies appear active, black holes appear active, star formation appears active, and now larger structures themselves may already be taking shape. The universe seems eager to build complexity wherever conditions allow. Yet among all these discoveries, another puzzle has begun attracting attention. If the formation of galaxies and larger structures appears difficult to explain, some individual galaxies are presenting an entirely different challenge. According to modern cosmology, dark matter should play a central role in the formation and stability of galaxies. In many ways, it acts as the invisible scaffolding upon which cosmic structures are built. But James Webb is beginning to reveal systems that seem strangely inconsistent with those expectations. Some galaxies appear to contain far less dark matter than astronomers would anticipate, raising questions about one of the most important ingredients in our understanding of the universe. And that mystery takes us directly to the next chapter of the story. By the time James Webb began revealing unexpectedly mature galaxies, oversized black holes, and signs of large-scale structures forming earlier than anticipated, astronomers were already confronting a growing list of puzzles. Yet another mystery soon emerged from a completely different direction. This one did not involve objects that appeared too large or too old. Instead, it involved something that seemed to be missing. And what appeared to be missing was one of the most important ingredients in modern cosmology: dark matter. Few ideas have transformed astronomy more profoundly than dark matter. Although nobody has directly observed it, its gravitational influence appears everywhere. Galaxies rotate too quickly for their visible matter alone to hold them together. Clusters of galaxies far more gravitational pull than their stars and gas can account for. Even the large-scale structure of the universe seems to require an invisible framework capable of guiding matter into the enormous cosmic web we observe today. According to current estimates, ordinary matter, the stars, planets, gas clouds, and galaxies we can see, accounts for only a small fraction of the universe's total contents. Dark matter appears to outweigh visible matter by more than 5 to 1. In many ways, modern cosmology treats dark matter as the hidden scaffolding of the universe. Long before galaxies fully formed, massive concentrations of dark matter were already shaping the cosmos. Ordinary matter gradually fell into these invisible gravitational wells, eventually creating stars and galaxies. Without dark matter, many of the structures observed throughout the universe would be difficult to explain. It is not merely another component of cosmic evolution. It is one of the foundations upon which that evolution is believed to depend. This is why certain observations have attracted so much attention. Over the past several years, astronomers have identified galaxies that appear unusually deficient in dark matter. Some examples were discovered before Webb launched, but James Webb's ability to study distant and faint systems in unprecedented detail is providing researchers with entirely new opportunities to investigate these strange objects. While Webb is not directly detecting dark matter itself, its observations are helping astronomers examine galaxies whose behavior does not always fit comfortably within existing expectations. At first glance, the idea sounds impossible. If dark matter is essential for building galaxies, how can a galaxy exist without much of it? It would be like discovering a skyscraper with no visible foundation. The building is clearly standing. The question is how. One possibility is that some galaxies lose a significant portion of their dark matter through violent interactions. The universe is not a peaceful place. Galaxies collide. They merge. They pass close enough to distort one another through immense gravitational forces. During such encounters, stars, gas, and dark matter may not all respond in exactly the same way. Over time, a galaxy might be stripped of much of its invisible mass, while retaining a substantial fraction of its visible stars. If this explanation is correct, then these unusual systems may simply represent survivors of extraordinary cosmic events. Yet even this raises further questions. If dark matter can be removed so efficiently under certain circumstances, how common are such processes? And how many similar systems might exist throughout the universe without our knowledge? Every answer seems to generate new uncertainties. What makes the situation particularly fascinating is that dark matter remains one of the greatest mysteries in all of science. Despite decades of effort, researchers still do not know what dark matter actually is. It does not appear to emit light. It does not appear to absorb light. It cannot be photographed directly. Its existence is inferred entirely through gravity. Astronomers can measure its effects, map its influence, and estimate its distribution, but its true nature remains unknown. In a sense, much of modern cosmology is built around something we know is there but do not fully understand. This means every unusual observation carries enormous significance. When astronomers find galaxies behaving in unexpected ways, they are not simply studying isolated objects. They are testing the foundations of entire theories. If dark matter behaves differently than expected, the consequences could ripple through our understanding of galaxy formation, structure, evolution, and even the history of the universe itself. James Webb is particularly valuable in this investigation because it allows astronomers to examine galaxies during much earlier periods of cosmic history. Rather than studying only mature systems in the nearby universe, researchers can now investigate galaxies that existed billions of years ago. This creates an opportunity to observe how dark matter may have influenced galaxy formation during the universe's earliest stages. If strange dark matter-deficient systems appear across different epochs, that pattern could provide important clues about the underlying mechanisms responsible for their existence. At the same time, Webb continues to reveal just how complicated galaxies can be. The old image of galaxies as simple collections of stars has largely disappeared. Modern observations show systems shaped by mergers, feedback processes, black hole activity, gas flows, magnetic fields, and countless other influences operating simultaneously. The more closely astronomers examine these objects, the more they resemble living ecosystems rather than static structures. Every galaxy carries a unique history written across billions of years. This complexity makes it difficult to draw simple conclusions. Some apparent challenges to dark matter models may eventually find explanations within existing theories. Others may reveal genuinely new physics. At this stage, researchers remain cautious. Extraordinary claims require extraordinary evidence, and astronomy has repeatedly demonstrated the importance of patience. The universe often appears stranger at first glance than it ultimately proves to be. Yet there is something undeniably intriguing about these observations. James Webb was expected to refine our understanding of galaxy formation. Instead, it keeps exposing new layers of uncertainty. Massive galaxies appear too early. Black holes grow too quickly. Large structures emerge sooner than expected. And now some galaxies seem oddly inconsistent with the invisible framework believed to support them. Each mystery alone might be manageable. Together they create the impression that the early universe still holds many secrets. But perhaps the most remarkable discovery of all is not a strange galaxy or an unusual black hole. It is the simple fact that James Webb is allowing humanity to look farther back in time than ever before. Every new distance record pushes our view closer to the beginning itself. And among all the ancient objects Webb has uncovered, one discovery stands above the rest because it represents the most distant galaxy ever confirmed. A glimpse of the universe so young that it challenges our ability to comprehend just how far back we are truly looking. For most of human history, distance and time were completely separate ideas. A mountain was far away because it occupied a distant place. A historical event belonged to the past because it happened long ago. Only in the last century did we fully realize that when it comes to the universe, distance and time are often the same thing. Every time astronomers look deeper into space, they are also looking further into the past. Light travels incredibly fast, but the universe is so enormous that even light requires billions of years to cross it. The farther away an object is, the older the image we receive becomes. James Webb was designed specifically to exploit this reality. Its mission was not merely to see distant galaxies. Its mission was to see ancient galaxies. It was built to push humanity's vision closer to the beginning of cosmic history than ever before, and eventually it succeeded beyond almost anyone's expectations. Among Webb's most remarkable discoveries is a galaxy known as JWST 14-0. The name itself sounds technical and forgettable, but what it represents is extraordinary. This galaxy currently holds the record as the most distant confirmed galaxy ever observed. The light reaching James Webb from this object began its journey approximately 13.5 billion years ago. By the time that light started traveling across the universe, our sun did not exist. Earth did not exist. The Milky Way had not yet reached anything close to its modern form. Even many of the galaxies surrounding us today were still in the earliest stages of development. When Webb observes JWST 14-0, it is seeing the galaxy as it existed only a few 100 million years after the Big Bang. The scale of this achievement is difficult to comprehend. Imagine compressing the entire history of the universe into a single calendar year. The Big Bang occurs at midnight on January 1st. The formation of Earth arrives in September. Dinosaurs appear in late December. Human civilization occupies only the final moments before midnight on December 31st. JWST 14-0 would belong to the first few days of January. It exists so close to the beginning that it effectively serves as messenger from the universe's earliest chapters. For decades, astronomers dreamed about finding galaxies this distant. The challenge was not simply one of sensitivity. The expansion of the universe stretches light as it travels. The farther a galaxy lies, the more its light shifts toward longer wavelengths. Eventually, visible light becomes infrared light. By the time the oldest galaxies are observed, much of their original radiation has been stretched beyond the reach of traditional optical telescopes. This is one of the primary reasons James Webb was built as an infrared observatory. It was specifically designed to detect these ancient signals. What surprised researchers was not merely that Webb found such distant galaxies. It was what those galaxies appeared to be. JWST 14-0 is not some faint, barely detectable smudge hovering at the edge of observability. Instead, it appears brighter and more substantial than many scientists expected. Once again, Webb was encountering a familiar pattern. The earliest universe seemed unexpectedly active. The galaxy contains evidence of significant star formation. It appears larger and more developed than many models predicted for an object existing at such an early stage of cosmic history. The farther back astronomers look, the more they keep encountering the same unsettling theme. Complexity appears early. This does not necessarily mean our cosmological models are wrong, but it does suggest that certain processes may have been operating more efficiently than expected. Stars may have formed rapidly, gas may have collapsed faster, structure formation may have progressed with surprising speed. Whatever the explanation, the universe keeps presenting astronomers with mature-looking systems at astonishingly young ages. The discovery also highlights something remarkable about James Webb itself. For decades, the earliest observable galaxies existed largely as theoretical targets. Scientists knew they should be there, but actually detecting them remained extraordinarily difficult. Webb transformed those targets into real objects. What was once speculation became observation. Entire regions of cosmic history that previously existed as blank spaces are now filled with data. And yet every answer seems to create another question. Because JWST 14-0 is unlikely to be the final record holder, there is a good chance that even more distant galaxies remain hidden beyond Webb's current discoveries. Every deep field survey pushes farther into the past. Every improvement in analysis techniques reveals fainter objects. Every new observation expands the frontier. Somewhere beyond the galaxies already identified may lie systems that formed even closer to the beginning itself. This creates an extraordinary possibility. Humanity may be approaching the point where we can directly observe the transition between darkness and light in the early universe. Before the first stars existed, the cosmos was a very different place. Following the Big Bang, the universe eventually cooled enough for atoms to form. Light could travel freely, but there were no stars yet to illuminate space. For millions of years, the cosmos entered a period often called the cosmic dark ages. The universe was filled with hydrogen and helium, but there were no galaxies, no planets, and no visible sources of light. Gravity was quietly at work, gathering matter into denser regions, preparing the conditions necessary for the first stars to ignite. Eventually, something changed. The first stars switched on, the first galaxies emerged, the darkness began to end. This transition represents one of the most important events in cosmic history, because it transformed the universe from a relatively simple environment into one increasingly filled with structure, radiation, and complexity. Yet despite its importance, many details remain poorly understood. Astronomers still debate exactly when it happened, how rapidly it unfolded, and what the earliest galaxies actually looked like. James Webb is now providing humanity's best opportunity to answer those questions. Every new distance record brings researchers closer to witnessing the moment when the first luminous structures began reshaping the cosmos. Objects like JWST 14-0 are not merely distant galaxies. They are signposts pointing toward one of the greatest transitions in the history of the universe. They represent a bridge between the familiar cosmos we inhabit today and a much stranger universe that existed near the beginning. And as Webb continues pushing deeper into the past, another realization is becoming increasingly difficult to ignore. The earliest galaxies were not just appearing sooner than expected. They were also behaving in ways that suggest the period known as cosmic dawn may have been far more complicated than astronomers once imagined. Instead of a simple and gradual awakening, the universe's first age of light may have been a surprisingly chaotic and remarkably sophisticated era. And that brings us to another mystery that James Webb is only beginning to uncover. For generations, astronomers imagined cosmic dawn as one of the simplest periods in the history of the universe. It was supposed to be a transitional era, a brief chapter between darkness and structure, a time when the first stars flickered into existence and the first primitive galaxies slowly emerged from an otherwise empty cosmos. The picture was relatively straightforward. Following the Big Bang and the long cosmic dark ages, gravity gradually gathered matter into dense pockets. Those pockets produced the first stars. The first stars illuminated their surroundings. The first galaxies assembled. Complexity would come later. At least that was the expectation. James Webb is revealing something very different. The deeper scientists look into cosmic dawn, the less it resembles a quiet beginning, and the more it resembles a universe already bursting with activity. Instead of finding a handful of isolated objects struggling to form, Webb is discovering galaxies producing stars at astonishing rates, black holes growing rapidly, and systems that appear far more organized than many models predicted. Once again, the challenge is not that these things can happen. The challenge is that they seem to be happening almost immediately after the universe becomes observable. To understand why this matters, it helps to appreciate how dramatic cosmic dawn actually was. Before the first stars existed, the universe was a remarkably dark place. Matter filled space, but there were no stars to shine, no galaxies to illuminate the void, and no planets reflecting light. Hydrogen gas dominated the cosmos. Gravity was quietly shaping the future, but almost nothing visible existed. Then, somewhere within that darkness, the first stars ignited. For the first time since the aftermath of the Big Bang, new sources of light appeared. These stars began flooding the universe with radiation, transforming their surroundings and setting into motion processes that would ultimately lead to galaxies, planets, and life itself. For many years, astronomers expected this transformation to unfold gradually. The first stars would appear, small galaxies would follow, larger structures would emerge much later. Cosmic dawn was imagined as a slow sunrise. James Webb is increasingly making it look more like an explosion of activity. One reason for this is the sheer number of luminous objects Webb is finding at extraordinary distances. Many researchers anticipated that the earliest observable galaxies would be relatively rare. Instead, deep field observations have revealed surprisingly rich populations of galaxies existing during the first few 100 million years of cosmic history. Every new survey seems to uncover additional objects, pushing the boundaries of what scientists thought was possible. The universe's first billion years are beginning to look far more crowded than expected. This abundance has important implications because the first galaxies played a crucial role in a process known as reionization. Shortly after atoms formed in the early universe, hydrogen gas filled much of space in a neutral state. Neutral hydrogen has an important property. It absorbs certain wavelengths of light. In effect, it can act like a cosmic fog. At some point, Radiation from the first stars and galaxies began stripping electrons away from these hydrogen atoms, transforming them into ionized plasma. As this happened, the fog gradually cleared. Light could travel more freely through the universe. Astronomers refer to this transformation as the epoch of reionization, and it represents one of the most significant transitions in cosmic history. The mystery is that researchers are still trying to determine exactly what caused it. For years, many models suggested that large numbers of small galaxies working together provided enough radiation to drive reionization. Yet James Webb is discovering galaxies that appear brighter and more active than expected. Some astronomers now wonder whether the earliest galaxies contributed more to this process than previously believed. Others suggest that active black holes may have played a larger role. The debate remains unresolved, but Webb's observations are forcing scientists to reconsider the balance of power during cosmic dawn. And then there is the issue of scale. Many of the galaxies Webb is finding are not simply producing stars. They are producing stars at extraordinary rates. Some appear capable of generating dozens or even hundreds of solar masses worth of stars every year. To put that into perspective, the Milky Way currently forms only a few solar masses worth of stars annually. Yet, certain galaxies observed during cosmic dawn seem to be operating at a pace that would be impressive even in the modern universe. The implication is difficult to ignore. The earliest galaxies may have been sites of intense and highly efficient star formation, converting gas into stars with remarkable speed. This growing complexity is creating a fascinating dilemma for cosmologists. The closer researchers move toward the beginning of the universe, the more they expect simplicity. Yet, James Webb repeatedly reveals systems that appear surprisingly sophisticated. It is almost as if complexity arrived ahead of schedule. Galaxies are not merely appearing, they are interacting, evolving, enriching themselves with heavier elements, and contributing to large-scale cosmic transformations. The early universe increasingly resembles a dynamic ecosystem rather than a primitive frontier. Of course, caution remains essential. Astronomy has a long history of apparent surprises that eventually found explanations within established physics. It is entirely possible that future observations will show that cosmic dawn was always capable of producing such complexity. Improved simulations may eventually reproduce much of what Webb is observing. Yet even if that happens, the discoveries remain extraordinary because they are revealing details of an era humanity has never been able to study directly before. In many ways, cosmic dawn is becoming one of the most important laboratories in modern astronomy. It represents the period when the first structures transformed the universe from darkness into light. Understanding what happened during those hundreds of millions of years means understanding the foundations of everything that followed. Every galaxy, every star, every planet, and every living organism ultimately traces its origins back to processes unfolding during this remarkable era. And yet perhaps the most surprising lesson from James Webb is that cosmic dawn was not simply the birth of galaxies. It may also have been the beginning of environments far more diverse than anyone imagined. Because while Webb has been transforming our understanding of the early universe, it has also been making astonishing discoveries much closer to home. Some of those discoveries involve planets orbiting distant stars, worlds with atmospheres containing chemicals and structures that challenge existing expectations. In fact, some of the strangest mysteries uncovered by James Webb are not ancient galaxies at all, but exoplanets whose atmospheres seem almost impossible. For most of its mission, James Webb has been associated with distant galaxies, ancient stars, and the earliest chapters of cosmic history. The telescope was designed to look billions of years into the past, allowing humanity to observe events that occurred near the beginning of the universe itself. Yet some of Webb's most intriguing discoveries have come from a completely different direction. Instead of looking billions of light years away, astronomers have turned the telescope toward planets orbiting nearby stars. And in doing so, they have uncovered atmospheres that seem far stranger than many scientists expected. At first glance, exoplanets might appear unrelated to the mysteries of cosmic dawn. One concerns the earliest galaxies in the universe. The other concerns worlds orbiting stars within our own cosmic neighborhood. But both are connected by the same fundamental question: how common is complexity in the universe? James Webb is revealing that complexity emerged surprisingly early among galaxies. and it is also revealing that planetary environments may be far more diverse than anyone previously imagined. Before Webb launched, astronomers already knew that exoplanets were common. Thousands had been discovered using a variety of techniques. Some were rocky worlds similar in size to Earth. Others were giant gas planets larger than Jupiter. Some orbited close to their stars, while others traveled along distant, frozen paths. Yet, despite the growing catalogue, scientists knew remarkably little about what many of these worlds were actually like. Detecting a planet is one thing. Studying its atmosphere is something else. The challenge comes down to scale. A planet is tiny compared to its host star. Even the largest exoplanets are often overwhelmed by the brightness of the stars they orbit. Trying to study an atmosphere around such a distant world is a little like trying to determine the color of a moth flying in front of a lighthouse. From thousands of miles away, the signal is incredibly faint. James Webb changed that. One of the telescope's greatest strengths is its ability to analyze infrared light with extraordinary precision. When a planet passes in front of its star, a small fraction of the starlight filters through the planet's atmosphere before reaching Webb. Different molecules absorb different wavelengths of light. By carefully measuring these patterns, astronomers can determine which chemicals are present in the atmosphere. It is an astonishing achievement. Humanity has reached the point where it can identify the molecular composition of air surrounding worlds dozens, hundreds, or even thousands of light years away. And some of those atmospheres have turned out to be extremely strange. One of the first major breakthroughs came from observations of WASP 39b, a giant gas planet orbiting a star roughly 700 light-years from Earth. This world is not remotely habitable. It is a scorching hot giant with temperatures high enough to melt many metals. Yet Webb's observations revealed something remarkable, clear evidence of sulfur dioxide in its atmosphere. This was the first definitive detection of the molecule on an exoplanet. More importantly, it provided direct evidence of photochemistry, a process in which stellar radiation triggers complex chemical reactions in an atmosphere. This may sound technical, but the implications were profound. Scientists were no longer simply detecting gases. They were beginning to observe active atmospheric chemistry unfolding on distant worlds. Then came even more intriguing discoveries. Webb detected water vapor in multiple exoplanet atmospheres. It identified carbon dioxide with unprecedented clarity. Methane appeared in some systems. Carbon-bearing compounds appeared in others. Every observation expanded the picture. Instead of finding simple atmospheres composed of one or two dominant gases, astronomers were increasingly discovering chemically rich environments shaped by complex interactions between radiation, temperature, pressure, and atmospheric circulation. Yet among all these observations, a handful of planets generate a particularly intense interest. One example is K218b, a world roughly 120 light-years away in the constellation Leo. This planet occupies a region around its star, often called the habitable zone, where temperatures may allow liquid water to exist under certain conditions. K218b is larger than Earth but smaller than Neptune, placing it in a category unlike anything found in our own solar system. For years, astronomers debated what such worlds might actually be like. Were they giant rocky planets, miniature gas giants, something entirely different? And James Webb's observations suggested the presence of methane and carbon dioxide in the atmosphere, while simultaneously finding little evidence for ammonia. These findings fueled discussions about a possible class of worlds known as Haitian planets, ocean-covered planets with hydrogen-rich atmospheres. Some researchers even proposed that certain chemical signatures might be consistent with processes that on Earth can be associated with biological activity. It is important to emphasize that no evidence of life has been confirmed. The observations remain the subject of active scientific debate, and many alternative explanations exist. Yet the fact that such discussions are even possible illustrates how dramatically Webb has transformed exoplanet science. Only a few decades ago, humanity did not know whether planets existed around other stars at all. Today, astronomers are debating the atmospheric chemistry of worlds located over 100 light-years away. What makes these discoveries particularly fascinating is that they reveal how diverse planetary environments can be. For generations, our understanding of planets was shaped almost entirely by the solar system. We had rocky worlds like Earth and Mars, gas giants like Jupiter and Saturn, and icy bodies in the outer regions. It was natural to assume that most planetary systems followed similar patterns. James Webb is showing that reality may be far more complicated. Some exoplanets orbit so close to their stars that their atmospheres are being stripped away by intense radiation. Others appear wrapped in thick layers of clouds, unlike anything found in the solar system. Some worlds experience temperatures exceeding 1,000 degrees Celsius. Others may contain deep global oceans beneath vast hydrogen atmospheres. Every observation seems to reveal another category of planet that nobody anticipated a generation ago. In a sense, the telescope is doing for planetary science what it has already done for cosmology. It is revealing that the universe contains more diversity, more complexity, and more surprises than our previous models suggested. The same instrument, uncovering mysteries near the beginning of time, is also uncovering mysteries surrounding worlds orbiting nearby stars. And among all the chemicals Webb is finding, one stands out above the rest. Again and again, astronomers keep encountering evidence of a molecule that plays a central role in the story of planets, stars, and life itself. It appears in planetary atmospheres, it appears in protoplanetary disks, it appears in molecular clouds between the stars. In fact, James Webb is increasingly revealing that this substance may be far more common throughout the universe than we once imagined. That substance is water, and its unexpected abundance has become another of the telescope's most fascinating mysteries. Few substances are more familiar to us than water. It fills our oceans, shapes our weather, carves mountains, sustains ecosystems, and makes life on Earth possible. Because it is so common in our daily experience, it is easy to forget how extraordinary water actually is. Every molecule consists of hydrogen and oxygen, elements forged through entirely different cosmic processes. Hydrogen emerged shortly after the Big Bang itself, while oxygen was created much later inside stars and scattered across space through stellar explosions. Every drop of water on Earth is therefore the product of billions of years of cosmic history. In a very real sense, water is not simply a feature of planets, it is a record of the universe's evolution. For decades, astronomers wondered just how common water might be beyond the solar system. The answer mattered enormously because water occupies a unique position in planetary science. It influences climate, geology, atmospheric chemistry, and potentially biology. Understanding where water exists helps scientists understand where complex environments may emerge. Before James Webb launched, evidence for water had already been detected in certain regions of space, but many important questions remained unanswered. How early did water appear in cosmic history? How widespread is it? And how does it move through the various stages of star and planet formation? James Webb is beginning to provide some remarkable answers. One of the telescope's most important capabilities is its ability to detect molecules through infrared spectroscopy. Different molecules leave distinctive fingerprints in light, allowing astronomers to identify their presence even across enormous distances. Water happens to produce particularly useful signatures in the infrared, making Webb an exceptionally powerful tool for tracing its distribution throughout the cosmos. What researchers are discovering is that water appears almost everywhere they look. The telescope has detected water vapor in exoplanet atmospheres, in planet-forming disks around young stars, in molecular clouds where new stars are being born, and even in some of the most distant environments ever studied. Rather than being a rare cosmic ingredient, water increasingly appears to be woven throughout the universe. One of Webb's most significant discoveries involved protoplanetary disks, the enormous rotating disks of gas and dust surrounding young stars. These disks represent planetary construction zones. Over millions of years, material within them gradually accumulates into planets, moons, asteroids, and comets. Understanding their composition is therefore essential for understanding how planetary systems form. Webb's observations revealed water vapor in regions where scientists believe rocky planets may eventually emerge. This finding was particularly exciting because it suggested that one of the key ingredients associated with habitability may be present during the earliest stages of planetary formation. Imagine watching a city being built and discovering that critical resources are already present at the construction site before most of the buildings even exist. That is essentially what Webb is revealing. Long before planets fully form, Water may already be part of the environment from which they emerge. The story becomes even more fascinating when we consider the solar system itself. For many years, scientists debated the origin of Earth's water. Did it form alongside the planet? Was it delivered later by comets? Did asteroids play the dominant role? The answer remains complex, but Webb's observations of distant planetary systems are providing valuable clues. By observing water in young disks around other stars, astronomers can study processes similar to those that may have shaped our own solar system billions of years ago. Yet water's presence raises another mystery. If water is so common, why are environments capable of supporting stable liquid water apparently much rarer? The answer lies in the delicate balance required for water to remain in liquid form. Too close to a star and it evaporates. Too far away and it freezes. Atmospheric conditions also matter. Planetary mass matters. Magnetic fields may matter. A world can contain enormous quantities of water while remaining entirely inhospitable to life as we know it. The existence of water alone does not guarantee habitability. It merely opens the door to possibilities. James Webb is helping astronomers explore those possibilities in unprecedented detail. Some of the most intriguing observations involve exoplanets whose atmospheres contain water vapor alongside other molecules such as methane and carbon dioxide. These chemical combinations provide important clues about atmospheric processes, planetary evolution, and potential environmental conditions. Every detection helps researchers build a more complete picture of how planets function beyond our own solar system. At the same time, Webb is revealing that water's story extends far beyond planets. Water appears in the giant molecular clouds where stars are born. It exists in icy grains drifting through interstellar space. It becomes incorporated into comets and asteroids. It survives within frozen regions of planetary systems. In many respects, water participates in a vast cosmic cycle. It forms, travels, freezes, evaporates, and reappears in new environments across billions of years. This realization has changed how many scientists think about the molecule. Water is no longer viewed simply as something that exists on certain planets. Instead, it is increasingly understood as a fundamental component of cosmic evolution itself. Wherever stars form, wherever planets emerge, wherever chemistry becomes more complex, water often seems to be present somewhere in the process. And yet some questions remain frustratingly unresolved. How early did substantial reservoirs of water appear in the universe? How efficiently is water incorporated into forming planets? How common are ocean-bearing worlds? Could entirely different types of habitable environments exist beyond those imagined from Earth's example? James Webb is providing unprecedented data, but every discovery seems to generate new mysteries alongside new answers. What makes the water mystery particularly compelling is that it connects nearly every scale of astronomy. It links stars to planets, galaxies to chemistry, and cosmic history to the conditions necessary for life. Few substances bridge so many different fields of research. The same molecule found in distant planetary atmospheres may also be present in ancient clouds that existed long before our solar system was born. Yet even as Webb traces water across the cosmos, it is uncovering another class of objects that seem almost disconnected from everything around them. These are worlds that do not orbit stars in the conventional sense. They wander through space alone, drifting through the darkness without a permanent home. Some may have been ejected from planetary systems, others may have formed in isolation. Whatever their origin, they represent some of the strangest objects James Webb has observed so far, and their existence raises a simple but profound question. What happens when a planet has no star at all? When most people imagine a planet, they picture something familiar. A world orbiting a star, following a predictable path through space, while receiving light and heat from its parent sun. Every planet in our solar system follows this pattern. Mercury circles the Sun, Earth circles the Sun, Neptune circles the Sun. Even the countless exoplanets discovered over the past few decades have generally been found because they orbit stars. In many ways, the connection between a planet and a star seems so fundamental that it feels almost impossible to separate the two. James Webb is helping reveal a universe where that assumption may not always be true. Scattered throughout the darkness between stars are objects known as rogue planets, worlds that appear to drift through space without being permanently bound to any stellar system. These are planets without sunrises, planets without sunsets, planets that travel through an almost endless night. For years, astronomers suspected such objects existed, but studying them was extraordinarily difficult. Rogue planets are faint, cold, and isolated. Without a nearby star illuminating them, they become some of the hardest objects in the universe to detect. Yet James Webb is beginning to change that. One of the most intriguing regions examined by the telescope is the Orion Nebula, one of the nearest and most active stellar nurseries in the Milky Way. Located roughly 1,350 light-years from Earth, Orion contains vast clouds of gas and dust where new stars are continuously being born. It is a chaotic environment filled with gravitational interactions, stellar winds, radiation, and countless young objects competing for material. If there is a place where unusual worlds might emerge, Orion is an excellent candidate, and Webb found something unexpected there. Among the stars and protostars, astronomers identified numerous free-floating objects with masses comparable to giant planets. Some appeared to possess masses similar to Jupiter. Others may have been somewhat larger. What made them remarkable was that they did not seem to orbit any obvious star. Instead, they appeared to exist independently, drifting through space as isolated worlds. Some researchers refer to these objects as planetary mass bodies, while others debate whether certain examples should be classified as planets, failed stars, or something in between. The terminology remains controversial. What is not controversial is the fact that James Webb is revealing populations of free-floating objects that challenge traditional ideas about planetary systems. The obvious question is how such worlds form. One possibility is that many rogue planets begin life in ordinary planetary systems. Planet formation is a violent process. Young systems contain countless interactions between planets, gas disks, and stars. Gravitational encounters can become chaotic. In some cases, giant planets may scatter one another onto unstable trajectories. A close encounter with another massive world can effectively slingshot a planet out of its system entirely. Instead of remaining in orbit, the planet is ejected into interstellar space. If this mechanism is common, the galaxy may be filled with orphaned planets wandering through the darkness. Imagine a crowded city where occasional conflicts launch individuals beyond the city limits forever. Over billions of years, the population of wanderers could become enormous. Some estimates suggest there may be billions of rogue planets within the Milky Way alone. Yet ejection may not be the whole story. Some astronomers suspect that certain rogue worlds form independently, without ever belonging to a stellar system in the first place. In regions like the Orion Nebula, collapsing clouds of gas may occasionally produce objects too small to ignite nuclear fusion. They never become stars. Instead, they form directly as isolated planetary mass objects. If this is true, then some rogue planets were never planets in the traditional sense. They were born alone. This distinction matters because it blurs one of the most important boundaries in astronomy, the boundary between planets and stars. For generations, these categories appeared relatively straightforward. Stars generate energy through fusion. Planets do not. Yet nature rarely respects human classifications. Between the smallest stars and the largest planets exists a vast grey area populated by brown dwarfs, substellar objects, and potentially free-floating worlds whose origins remain uncertain. James Webb is revealing just how crowded that grey area may be. One particularly surprising discovery involved pairs of free-floating planetary mass objects found together. These systems, informally nicknamed Jupiter mass binary objects, appeared to consist of two isolated worlds orbiting one another without an accompanying star. The discovery was unexpected because conventional formation models struggle to explain how such systems could emerge and remain stable. It was as if astronomers had discovered miniature planetary systems floating through space entirely on their own. The existence of these objects raises fascinating questions. How many rogue worlds are there? Are they rare exceptions or common products of cosmic evolution? Could some possess atmospheres, weather systems, or even internal heat sources, despite lacking a star? And perhaps most intriguingly, could certain rogue planets remain surprisingly warm beneath thick atmospheres or hidden oceans, sustaining environments far different from anything found in the solar system? While such possibilities remain speculative, they highlight how dramatically Webb is expanding our understanding of planetary diversity. For centuries, planets were viewed as companions of stars. Now, astronomers are increasingly realizing that some worlds may spend billions of years traveling alone through interstellar space. In a strange way, rogue planets represent the opposite extreme of everything James Webb has been discovering. Earlier mysteries involved galaxies assembling too quickly, black holes growing too rapidly, and large-scale structures emerging earlier than expected. Those discoveries revealed a universe filled with organization and complexity. Rogue worlds reveal a universe equally capable of producing isolation. Entire planets can exist without solar systems. Worlds can drift through the darkness between stars, carrying their secrets across unimaginable distances. Yet even these lonely wanderers are connected to a larger story. Whether rogue planets form independently or are ejected from planetary systems, they ultimately originate from the same process that creates stars, planets, and entire solar systems. Understanding their existence means understanding how planetary systems themselves are built, and that brings us to another mystery James Webb is helping uncover. Because the telescope is revealing evidence that planets may form far faster and in far more complex ways than astronomers once believed. Some young planetary systems already appear astonishingly organized long before they should. The structures emerging within these cosmic construction zones are forcing scientists to rethink how planets come into existence in the first place. For much of modern astronomy, planet formation was viewed as a relatively slow process. A young star would emerge from a collapsing cloud of gas and dust, surrounded by a rotating disk of leftover material. Over millions of years, tiny dust grains would collide and stick together. Those grains would become pebbles. Pebbles would become rocks. Rocks would become planetesimals. Planetesimals would gradually merge into planetary embryos, and eventually entire planets would emerge. It was a logical sequence, supported by decades of theoretical work. The details remained complicated, but the overall picture appeared reasonably well understood. Then astronomers started looking more closely. Even before James Webb launched, powerful observatories such as ALMA had begun revealing something surprising. Around certain young stars, enormous disks of gas and dust already contained rings, gaps, spirals, and other structures that seemed far more organized than expected. Some of these systems appeared so mature that they looked as though planets were already shaping them. The problem was that many of the stars involved were extremely young. According to conventional timelines, there should not have been enough time for large planets to form and begin sculpting their surroundings. James Webb has added a completely new level of detail to this mystery. Using its infrared instruments, the telescope can peer through dust clouds that block visible light, allowing astronomers to study the inner regions of planet-forming systems with unprecedented precision. These are the environments where planets are actively being assembled. Rather than observing finished worlds, Webb is effectively watching the construction process itself, and what it is seeing is remarkably complex. Many protoplanetary disks appear highly structured even at very early stages of development. Instead of smooth distributions of gas and dust, researchers often find intricate patterns suggesting that powerful processes are already underway. Some disks contain sharply defined gaps, others display bright rings. Still others show asymmetrical features that are difficult to explain through simple models of gradual accumulation. Imagine visiting a construction site shortly after work begins and discovering roads, foundations, and entire neighborhoods already taking shape. The structures themselves are not impossible. The question is why they seem to be appearing so quickly. That question sits at the center of one of the biggest debates in planetary science. How fast can planets actually form? For years, the standard view assumed that building large planets required millions of years. Dust particles are incredibly small. Growing them into planetary bodies is not an easy task. Many collisions result in fragmentation rather than growth. Gas disperses over time. Young stars produce radiation and stellar winds capable of disrupting their surrounding disks. Planet formation faces numerous obstacles, yet observations increasingly suggest that nature may be more efficient than expected. Some models now propose that under the right conditions, material within a disk can rapidly concentrate into dense regions. These concentrations may collapse much faster than traditional theories predicted, accelerating the formation of planetary cores. Other models emphasize the role of inabilities within the disk itself, processes capable of reorganizing matter on surprisingly short timescales. James Webb is providing critical evidence for these ideas because it can directly observe the chemistry and structure of disks during their earliest stages. Researchers are no longer relying solely on simulations. They are beginning to watch planetary systems evolve in real time. One of the most important discoveries involves the distribution of molecules throughout these disks. Webb has detected water vapor, carbon-bearing compounds, and other chemicals in regions where rocky planets may eventually emerge. This is significant because planetary composition depends heavily on the materials available during formation. The chemistry of a young disk helps determine the chemistry of future planets. In other words, Webb is not just showing us where planets form, it is showing us what they may be made of. This has profound implications because planetary systems appear far more diverse than astronomers once imagined. For much of the 20th century, our solar system served as the primary template for understanding planetary formation. Rocky planets occupied the inner regions, gas giants formed farther out. The arrangement seemed natural. Then exoplanet discoveries changed everything. Hot Jupiters orbiting extremely close to their stars, super-Earths larger than any rocky planet in our solar system, mini Neptunes occupying entirely unfamiliar categories, compact systems containing multiple planets packed into regions smaller than Mercury's orbit. Every new discovery challenged assumptions that once appeared obvious. James Webb is now helping explain how such diversity becomes possible. Rather than following a single universal blueprint, planetary systems may emerge through a wide range of pathways. Small differences in disk mass, temperature, chemistry, turbulence, and stellar activity can produce dramatically different outcomes. Two stars born from similar clouds may ultimately host completely different planetary architectures. The more researchers learn, the more planet formation resembles an ecosystem rather than a simple assembly line. This growing complexity is remarkably similar to what Webb has already revealed about galaxies and black holes. Again and again, the telescope is uncovering systems that are more dynamic, more varied, and more efficient than expected. The universe appears exceptionally good at generating complexity. Yet another mystery remains hidden within these disks, because alongside the gas, molecules, and forming planets exists something that should not be there in the quantities Webb is finding. Tiny particles scattered throughout the early universe are creating one of the most persistent puzzles in modern astronomy. These particles may seem insignificant compared to galaxies or black holes, but they influence everything from star formation to planetary development. They are cosmic dust, and according to James Webb, there may have been far more of it in the early universe than anyone expected. When people imagine the great mysteries of the universe, they usually think about black holes, dark matter, or distant galaxies. Very few would expect one of the biggest puzzles uncovered by James Webb to involve something as seemingly insignificant as dust. After all, dust sounds ordinary. It gathers on shelves, drifts through sunlight, and accumulates in forgotten corners of rooms. Yet on cosmic scales, dust is one of the most important substances in existence. It helps form stars, it helps build planets, it influences the chemistry of galaxies. It absorbs light, reshapes observations, and plays a crucial role in nearly every stage of cosmic evolution. And according to James Webb, there appears to have been far more dust in the early universe than anyone expected. At first glance, this might not sound like a major problem. Dust exists throughout the modern universe. The Milky Way contains enormous clouds of it. Young stars are surrounded by dusty disks. Entire galaxies glow with radiation emitted by warm dust particles. Astronomers have studied cosmic dust for decades. The issue is not that dust exists. The issue is how quickly it seems to appear. To understand why this matters, we need to understand where dust comes from. Immediately after the Big Bang, there was no dust at all. The early universe contained mostly hydrogen and helium. The heavier elements necessary for dust formation did not yet exist. Carbon, oxygen, silicon, magnesium, iron, and other ingredients had to be manufactured inside stars. Only after those stars lived, evolved, and died could those elements be released into space. Once present, they could combine into tiny solid particles that astronomers collectively refer to as cosmic dust. This means dust should take time to accumulate. First, stars must form. Those stars must create heavier elements. The stars must die. The elements must be released. The particles must condense. Only then can significant quantities of dust emerge. Every step requires time. Yet James Webb keeps finding galaxies that appear surprisingly dusty when the universe was still remarkably young. This creates a familiar problem. The clock once again seems too short. Many distant galaxies observed by Webb show evidence of substantial dust reservoirs only a few 100 million years after the Big Bang. Some appear far more chemically evolved than expected. Their light suggests environments where dust has already become an important component of the galaxy itself. In some cases, the amount of dust inferred from observations is difficult to reconcile with traditional timelines of stellar evolution. Imagine discovering a vast desert shortly after a planet forms. The sand itself is not mysterious. The mystery is how the processes required to create it could have occurred so quickly. That is essentially the situation astronomers face. The dust is there. The question is how it arrived so early. One possible explanation involves supernovae. Massive stars live fast and die young. Unlike smaller stars which can survive for billions of years, the most massive stars may exhaust their fuel in only a few million years. When they explode as supernovae, they release enormous quantities of heavy elements into surrounding space. Some researchers argue that these explosions could have produced dust much more efficiently than previously assumed. At first, this seems like a promising solution. Massive stars form, they die quickly, they produce dust. Problem solved. Unfortunately, the situation is not that simple. Supernovae are capable of creating dust, but they are also capable of destroying it. The shock waves generated by these explosions can shatter existing dust grains and disperse material throughout the surrounding environment. In some cases, the same event that creates dust may simultaneously eliminate a significant portion of it. As a result, astronomers continue debating whether supernovae alone can explain the quantities Webb is observing. This has led researchers to consider additional mechanisms. Perhaps dust formation occurs more efficiently inside young galaxies than expected. Perhaps the earliest stars were fundamentally different from stars today. Perhaps stellar populations in the early universe evolved at extraordinary rates. Or perhaps there are processes contributing to dust production that current models still underestimate. The fact that multiple explanations remain viable highlights just how unresolved the mystery remains. What makes the dust problem particularly important is that dust affects far more than the appearance of galaxies. Dust influences almost every stage of cosmic evolution. It helps cool gas clouds, making star formation easier. It participates in chemical reactions. It becomes incorporated into planets, moons, asteroids, and comets. Without dust, many of the structures we take for granted throughout the universe would be difficult to produce. In a sense, dust acts as a bridge between generations of stars. One generation creates the raw materials. The next generation inherits them. Planets eventually emerge from the leftovers. The existence of large amounts of dust therefore suggests that significant stellar activity has already occurred. It serves as evidence that previous generations of stars have lived and died. Every dusty galaxy carries a record of earlier cosmic history. This is why Webb's observations are so intriguing. The telescope is not simply finding dust. It is finding evidence that the cycle of stellar birth, evolution, and enrichment may have been operating far earlier than expected. Once again, the universe appears to have become chemically complex with astonishing speed. And there is another consequence. Dust has a habit of hiding things. Astronomers often think of dust as both a source of information and an obstacle. While dust reveals chemical evolution, it also absorbs and scatters light. Entire regions of galaxies can be concealed behind dusty clouds. Objects that appear faint may actually be much brighter than they seem. In some cases, dust can effectively hide entire populations of stars and galaxies from view. For decades, this limitation affected nearly every attempt to study the early universe. Traditional telescopes operating primarily in visible light often struggled to see through dusty environments. Entire categories of objects may have remained invisible simply because their light never reached us clearly. This is one reason James Webb is so powerful. Its infrared instruments can penetrate dust far more effectively than many previous observatories. The telescope is revealing objects that were previously hidden behind cosmic veils, allowing astronomers to see deeper into ancient galaxies than ever before. And that realization leads directly to another possibility. If the early universe contained more dust than expected, then perhaps it also contains more galaxies than expected. Entire populations of ancient galaxies may have remained hidden from previous observations, concealed behind clouds of dust for billions of years. If so, James Webb may not simply be revising our picture of the early universe. It may be revealing that a significant fraction of that universe was hidden from us all along. And that possibility leads directly to one of the telescope's most fascinating discoveries: the growing evidence that countless ancient galaxies may still be waiting to be found. One of the most surprising lessons from the James Webb Space Telescope is that many of the universe's greatest mysteries may not involve the objects we can see. They may involve the objects we have been missing. For decades, astronomers worked with what seemed like a reasonable assumption. As telescopes improved, humanity's picture of the universe became increasingly complete. Larger telescopes revealed fainter galaxies. Better instruments pushed observations farther into space and further back in time. While researchers understood that some objects remained beyond detection limits, there was a general expectation that the broad outline of cosmic history was becoming clear. James Webb is forcing astronomers to reconsider that assumption. Again and again, the telescope is revealing galaxies that previous observatories either could not see at all or could only detect as faint, ambiguous signals. Entire populations of ancient objects are emerging from the darkness, suggesting that the early universe may have been far more crowded than scientists realized. This possibility is important because much of modern cosmology relies on counting galaxies. The number of galaxies present at different periods of cosmic history helps researchers understand how structure formed, how stars evolved, and how the universe changed over time. If large numbers of galaxies have been hidden from observation, then some of our conclusions about the early universe may require revision. To appreciate why this matters, imagine trying to understand the population of a city while only being able to observe the tallest buildings. You might correctly identify major districts and important landmarks, but you would miss countless homes, businesses, and neighborhoods hidden between them. Your map would not be completely wrong, but it would be incomplete. The same problem applies to astronomy. For years, telescopes were effectively seeing only the brightest portions of the distant universe. James Webb is now exposing much of what existed in the shadows. One reason these galaxies remained hidden involves the very dust discussed in the previous chapter. Dust absorbs and scatters visible light, making certain objects difficult to detect. Young galaxies experiencing intense bursts of star formation often generate large quantities of dust. Ironically, some of the most active galaxies in the early universe may have concealed themselves behind the very material produced by their own stars. To visible light observatories, they appeared faint or disappeared entirely. Webb's infrared instruments can penetrate much of that obscuration, allowing astronomers to uncover systems that remained effectively invisible for decades. The results have been remarkable. Deep surveys conducted by Webb continue to reveal unexpectedly large numbers of distant galaxies. Some are relatively small, others appear surprisingly massive. Some contain intense star-forming regions. Others show evidence of more mature stellar populations. Together, they paint a picture of an early universe far richer and more diverse than previously imagined. Rather than a sparse landscape populated by a few primitive galaxies, Webb is revealing a cosmos filled with activity. This growing population has important consequences for several mysteries already discussed throughout this series. Consider the problem of reionization during cosmic dawn. Astronomers have long debated which sources provided enough radiation to transform the neutral hydrogen filling the early universe into ionized plasma. If there were more galaxies than previously counted, then the answer may become easier to explain. Countless faint galaxies, each contributing a small amount of radiation, could collectively have played a major role in reshaping the cosmos. The same logic applies to galaxy formation itself. Some of the tension between observations and theory may partly arise because researchers were working with incomplete information. If a significant population of ancient galaxies remained hidden, then our picture of how structures assembled over time may have been missing important pieces. Webb is not simply finding new objects. It is helping fill gaps in the historical record of the universe. Yet this discovery creates another fascinating possibility. What if the galaxies James Webb is finding are still only a fraction of what actually exists? Even Webb has limits. Although it is the most powerful space telescope ever built, it cannot detect every object in the universe. Some galaxies are too faint. Others remain hidden behind even thicker layers of dust. Some may lie at distances so extreme that their signals approach the edge of detectability. Every time astronomers push deeper into a survey, new objects appear. The frontier keeps moving outward. This pattern has repeated throughout the history of astronomy. Every major improvement in observational technology has expanded the known universe. When Galileo pointed his telescope toward the sky, countless stars appeared where none had been visible before. Later telescopes revealed nebulae. Then they revealed other galaxies. Then they revealed galaxy clusters. Now James Webb is revealing populations of ancient galaxies that remained hidden until the present decade. History suggests that every time humanity believes it is approaching completeness, the universe demonstrates otherwise. What makes this realization particularly profound is that hidden galaxies do more than increase numbers. They change context. A galaxy never exists in isolation. Every newly discovered object affects our understanding of neighboring systems, cosmic environments, and the evolution of larger structures. Adding thousands or millions of previously unseen galaxies is not like adding extra dots to a map. It is more like uncovering entire continents that were missing from the chart. This is one reason astronomers are so excited about Webb's discoveries. The telescope is transforming observations into archaeology. Researchers are not merely looking at distant objects. They are reconstructing forgotten chapters of cosmic history. Every newly identified galaxy contributes another clue about what the universe was actually like during its earliest epochs, and the emerging picture is increasingly difficult to ignore. The early universe appears brighter, busier, and more complex than expected. Galaxies formed earlier. Black holes grew faster, dust accumulated rapidly, large-scale structures emerged sooner, and now it seems likely that entire populations of galaxies remained hidden from view until James Webb arrived. Yet among all the missing pieces of cosmic history, perhaps none is more important than one that astronomers have spent decades trying to find. Hidden galaxies can be discovered. Hidden black holes can be inferred. But there is another target that remains stubbornly elusive: the first stars themselves, the objects that ended the cosmic dark ages and began the process that ultimately created everything we see today, have never been directly confirmed. James Webb was built partly to find them, and despite all of its extraordinary discoveries, the search is still ongoing. Every mystery James Webb has uncovered ultimately points back toward a single moment in cosmic history: the little red dots, the unexpectedly mature galaxies, the giant black holes, the hidden populations of ancient galaxies, the rapid appearance of dust and heavy elements. Each discovery raises new questions, but all of them eventually lead to the same fundamental problem. What started all of this? Before galaxies could exist, stars had to form. Before black holes could grow, stars had to die. Before planets could emerge, stars had to manufacture the elements necessary to build them. Somewhere in the distant past, the universe produced its very first generation of stars. Finding those stars has become one of the most important goals of modern astronomy. The challenge is that no one has ever directly observed them. Astronomers have given these hypothetical objects a name: population 3 stars. The terminology sounds technical, but the idea is relatively simple. Stars are often divided into populations based on their chemical composition. Population I stars, such as the Sun, contain significant amounts of heavy elements. Population 2 stars are older and contain fewer heavy elements. Population 3 stars represent something entirely different. They would have formed before any heavy elements existed at all. They would have been born from nearly pure hydrogen and helium, the raw materials left behind by the Big Bang itself. In theory, these stars should have been unlike anything visible in the modern universe. Today's stars form inside environments already enriched by countless generations of previous stellar evolution. The gas clouds that produce modern stars contain carbon, oxygen, silicon, iron, and many other elements. Population 3 stars had none of those advantages. They emerged from a chemically primitive universe. Because of this, many models suggest they may have behaved very differently from stars forming today. One of the most fascinating possibilities is that these first stars were enormous. Without heavy elements to help cool collapsing gas clouds, Material in the early universe may have accumulated into far larger stellar masses than are commonly observed today. Some simulations suggest that certain population 3 stars could have reached hundreds of times the mass of the Sun. Such stars would have been extraordinarily bright. They would have burned through their fuel rapidly and died in spectacular explosions, enriching the universe with the first heavy elements ever created. In many ways, these stars were the original architects of cosmic complexity. Every oxygen atom in your lungs, every carbon atom in your body, every iron atom in your blood ultimately traces its origins back to ancient stars. Population 3 stars began that process. They transformed a universe composed mostly of hydrogen and helium into a universe capable of producing planets, chemistry, and eventually life. Without them, none of the later mysteries uncovered by James Webb would exist. And yet they remain frustratingly elusive. The problem is not simply distance. Population 3 stars lived during an extraordinarily early period of cosmic history. Most likely, they also lived very short lives. Massive stars burn their fuel quickly. If the first stars were indeed hundreds of times more massive than the Sun, many may have survived only a few million years before exploding. In cosmic terms, that is an eye blink. The stars themselves may have disappeared long before the galaxies we observe today fully emerged. This creates a difficult situation for astronomers. The objects they want to find may no longer exist. Instead, researchers often search for indirect evidence. Certain chemical signatures can hint at the influence of population 3 stars. Some galaxies may contain stars formed from material enriched by the first stellar generation. Particular patterns of heavy elements could reveal how those ancient stars lived and died. James Webb is helping identify such clues, but the evidence remains incomplete. At times, the search resembles forensic science more than traditional astronomy. Investigators arrive long after the event has occurred and attempt to reconstruct what happened using whatever traces remain behind. The crime scene is billions of years old. The witnesses are gone. Only fragments of evidence remain. Yet James Webb is providing opportunities that previous telescopes simply could not. By observing galaxies closer and closer to the beginning of cosmic history, Webb is pushing into the era where population 3 stars may have existed. Some of the distant galaxies already identified could potentially contain regions influenced by these primordial objects. Others may preserve chemical fingerprints pointing directly toward the first generation of stellar activity. Every new observation expands the search area. What makes the quest particularly important is that population 3 stars may hold the key to several mysteries already discussed throughout this series. If these stars were exceptionally massive, they could help explain the rapid appearance of heavy elements. Their explosive deaths could contribute to the dust problem. Their remnants might provide the seeds for some of the giant black holes discovered by James Webb. In a sense, finding the first stars would not solve just one mystery. It could help solve many of them simultaneously. This is why astronomers are so eager to identify them. The first stars represent the missing opening chapter of a story whose later chapters are becoming increasingly visible. Webb has revealed surprisingly mature galaxies. It has revealed ancient black holes. It has revealed evidence of rapid chemical evolution. But all those discoveries describe a universe that already possesses a certain level of complexity. Population 3 stars belong to the moment before that complexity emerged. They represent the transition between simplicity and structure, the transition between darkness and light, the transition between a universe containing only basic ingredients and a universe capable of producing everything that followed. And yet, despite years of searching, no confirmed population 3 star has been found. That fact alone is remarkable. James Webb has looked farther into the past than any telescope in history. It has shattered distance records, rewritten theories of galaxy formation, and uncovered mysteries across nearly every field of astronomy. Yet, one of the objects it was partly designed to find remains hidden. Perhaps the first stars are simply too rare. Perhaps they lived too briefly. Perhaps they are concealed within galaxies we have not yet fully understood. Or perhaps the universe still has surprises waiting in its earliest chapters. Whatever the answer, the search continues. And in many ways, that search perfectly captures the larger story of James Webb itself. Again and again, the telescope approaches what appears to be the edge of understanding, only to reveal new questions beyond it. Every discovery opens another mystery. Every answer uncovers another layer of uncertainty. Which brings us to the final chapter of this story, because after all the galaxies, black holes, rogue worlds, hidden structures, and ancient stars, there remains a collection of mysteries that James Webb still cannot fully explain. And those unresolved questions may ultimately prove to be the telescope's most important discoveries of all. When the James Webb Space Telescope launched on Christmas Day in 2021, it carried some of the highest expectations ever placed upon a scientific instrument. Decades of planning, engineering, testing, and international cooperation had culminated in a machine designed to answer some of humanity's oldest questions. How did the first galaxies form? When did the first stars appear? How did the modern universe emerge from the aftermath of the Big Bang? Many people imagined Webb would finally provide clarity. It would fill in the missing pieces. It would transform speculation into certainty. Instead, something unexpected happened. The telescope answered many questions, but it created even more. This is not a sign of failure, quite the opposite. Throughout the history of science, the most important discoveries are often the ones that reveal how much remains unknown. Every time humanity develops a more powerful way of observing reality, the universe responds by becoming more complicated. Galileo discovered mountains on the moon and countless unseen stars. Hubble revealed that the Milky Way was only one galaxy among billions. Modern observatories uncovered dark matter, dark energy, exoplanets, and black holes. James Webb is continuing that tradition. Rather than simplifying the universe, it is revealing new layers of complexity hidden beneath old assumptions. Perhaps the most famous example is the mystery of the little red dots. Years after their discovery, astronomers still debate what many of these objects actually are. Some may be compact galaxies undergoing intense star formation. Others may contain actively feeding black holes. Certain examples could represent entirely new categories of objects that current models struggle to describe. Every new observation improves our understanding, yet the puzzle remains incomplete. The red dots continue to challenge assumptions about how quickly galaxies and black holes appeared in the early universe. Then there are the galaxies themselves. Again and again, Webb has found systems that seem more mature than expected. Some appear larger than models predicted. Others seem capable of producing stars at extraordinary rates. Researchers have proposed numerous explanations, including improved measurements, faster star formation, and more efficient galaxy growth. Yet no single explanation has completely eliminated the tension. The universe's earliest galaxies still appear surprisingly advanced. The black hole mystery remains equally unresolved. Astronomers know supermassive black holes exist. They know black holes can grow through accretion and mergers. What remains uncertain is how some of them became so massive so quickly. Every proposed solution introduces new questions. Larger seed black holes help explain rapid growth, but require unusual formation conditions. Direct collapse models offer another pathway, but depend on environments that remain difficult to verify. Faster accretion rates help close the gap but push against theoretical limits. Webb has provided extraordinary data, yet the full story remains elusive. Even the search for the first stars continues. Population 3 stars occupy a unique place in astronomy because they represent the beginning of stellar history. Theoretically, they should have existed. The chemical evolution of the universe practically requires them. Yet despite all of Webb's capabilities, no confirmed population 3 star has been directly observed. Researchers continue searching for signatures, clues, and indirect evidence, but one of the telescope's most important targets remains hidden. The dust problem also persists. Galaxies in the early universe often appear richer in dust than expected. While supernovae and other mechanisms likely contribute to dust production, astronomers are still debating whether current models fully account for the quantities being observed. Once again, the issue is not that dust exists. The issue is timing. The universe keeps appearing chemically mature sooner than anticipated. And then there are the mysteries that may not yet have names. This is perhaps the most fascinating aspect of James Webb's mission. Many of the telescope's most significant discoveries were not predicted in advance. Scientists expected Webb to study early galaxies, but they did not expect the abundance of little red dots. They expected to observe cosmic dawn, but they did not expect so many surprisingly bright and developed systems. They expected answers. Instead, they found entirely new questions. That pattern will likely continue. The telescope is still early in its operational life. Compared to observatories like Hubble, which spent decades transforming astronomy, James Webb has only begun exploring the universe. Future observations will be deeper, more detailed, and more ambitious. New surveys will examine regions of space never studied before. Additional discoveries will emerge. Some current mysteries may eventually be solved. Others may become even more confusing. What makes this moment unique is that astronomy is experiencing something rare, a genuine period of uncertainty. Researchers are not simply refining details within an established framework. In several areas, they are actively debating whether important pieces of the framework itself need adjustment. Such moments do not happen often. Most scientific progress occurs gradually. Occasionally, however, new observations arrive that force scientists to pause and reconsider long-held assumptions. James Webb appears to be creating one of those moments. This does not mean the foundations of cosmology are collapsing. The Big Bang remains strongly supported by multiple lines of evidence. Dark matter continues to explain many observations. General relativity remains one of the most successful scientific theories ever developed. Yet science has never been about protecting existing ideas. It is about testing them. When observations disagree with expectations, reality wins. And reality is proving wonderfully stubborn. The deeper James Webb looks into the universe, the stranger that universe often becomes. Galaxies emerge earlier than expected. Black holes grow faster than expected. Chemical complexity appears sooner than expected. Entire populations of hidden objects emerge from regions previously thought empty. Time and again, the telescope reveals a cosmos that seems determined to resist simplicity. Perhaps that is the most important discovery of all. Not a galaxy, not a black hole, not a distant planet, but a realization for much of human history, people imagined that the greatest challenge in astronomy was seeing farther. Build a larger telescope, look deeper into space, and the answers would eventually appear. James Webb has shown that the universe does not work that way. Seeing farther does not necessarily make reality simpler. Sometimes it makes reality more mysterious. The telescope was built to explore the earliest chapters of cosmic history, and it has succeeded beyond expectations. Yet instead of delivering a finished story, it has uncovered a narrative filled with missing pages, unexplained events, and unresolved questions. The universe that James Webb is revealing appears older, faster, more active, and more complex than many scientists anticipated. Every discovery brings us closer to understanding our origins, but every discovery also reminds us how much remains unknown, and perhaps that is exactly what makes this era of exploration so extraordinary. Because somewhere beyond the next observation, beyond the next deep field image, beyond the next record-breaking galaxy, another mystery is already waiting, just as it always has. And if James Webb has taught us anything, it is that the universe is almost certainly stranger than we imagine.